Good morning, everyone. Thank you for coming. How do you enjoy the day so far? Yeah, it's great. So, first session, thank you for coming, and I'm going to speak about bugs. I'm going to speak about specifically C++ bugs, but some of the bugs that we'll see are not related specifically to C++, and the idea is not to do the bugs, but to avoid them. A few words about myself. I'm a lecturer at the Academic College of Tel-Aviv-Yaffo, also teaching at Tel-Aviv University, co-organizer of this core C++ conference that we're in, and a trainer and advisor, C++, but not only. Bugs. Nice work by AI. We all have them. But then the question is, where do they come from? I mean, what is the source? Why? How can we avoid them? And if we think about bugs, let's start with a bug that I had in 2011. Now the reason that I can remember something that I had in 2011 is because I wrote a blog post. And I encourage anyone here, usually, especially the young folks, write blogs. I mean, write blog posts because this is the way to remember things. I'm today too lazy to do that, so I don't do that anymore. I don't know, maybe I will come back to that. But anyhow, in 2011, I had a bug. We had a bug in a company that I work at, and the bug was that on the date, January 2nd, our systems crashed in a cycle, like crashed, restarted, worked, and then after a while crashed again. And when we explored that and tried to see what is the problem, we realized that there is a timer that is being rescheduled again and again too many times. And it was specifically on January 2nd. Didn't happen before. We tried that on our lab, and we actually could see that it happens also in a test environment. And at the same time, someone said, oh, I see a post by another company. I will not tell you the name of the company. It is named after a fruit that had a similar bug on their systems. And we said, okay, maybe it is related to the actual date. On January 3rd, the bug disappeared. Systems worked as they should, no crash. So yeah, in a way it depends. It relates to the date. But it was not because of the date when we realized what the bug is. The bug was that when you trigger a timer, you pass to the timer a callback function. The callback function, the signature was that the callback function should return a value. The value is being used by the timer mechanics for whether to reschedule the timer or not. And the callback that was sent and should not be void, should return a value, didn't return a value. And when you have a function that should return a value and do not return a value, then the value, it's not a compilation error, by the way. If it was a compilation error, that would be good, because we would have catch that on time. But it is not. By the way, it is a very simple warning, but that warning was not set. We should have that warning. It was not in the warning flags. And when you have a function that should return a value and it doesn't, it just takes the value from the register that has the return value, and there is some value there, but it's not the value that you actually meant to. It's just, garbage, something that was there. And on January 2nd, yeah, it depends on the date, because for some reason, the timer is using date, and somewhere there, the register hold the value. So we did two things when we caught the bug. First, we grep. We look for all the timers in the system, whether we have the same thing in all timers in the system, right? And I'm taking that as the bug fix plus doing things to avoid the bug in other places. Emails to everybody, look, this is the bug, avoid this bug, make sure that all functions that should return value actually return a value. And we did another thing. We started running our systems 30 days ahead in a test environment. One was really realized that bugs might be related to the date. And we assumed that 30 days would be enough to solve any bug that we may find that relates to date. So this is an idea that maybe you can use in your systems as well. And this bug was waiting in my blog post to come up in this conference. And here it is. And I'm proud of that bug in a way. I mean, not of the bug. We shouldn't do such bugs, but I mean, it's a nice story. Let's speak about bugs. Bugs can relate to essence or accident. There is a very famous paper by Fred Brooks, 1986, where he differentiates between the essence of software development and the accident. Accident means anything that relates to the programming language, the tools, but it's not the essence of the problem, okay? And his argument, Fred Brooks, 1986, is that in decade from 1986, there wouldn't be any new tool, new paradigm that will shift the productivity of software development by a significant amount, like being more productive. It is said that he was right not only for a decade, but for more. I don't think that there is something that changed the productivity of developers. Maybe AI will, but I don't know, code completion, better IDEs, better static analyzers, etc. None of them is order of magnitude of a change. And his argument was that software development is related to accident. I mean, if something doesn't work, it might be that, oh, something I didn't think of in the language, or there is a tool that may help. Okay, this is the accident part, but the essence part is the actual problem domain. And the problem domains that we deal with are complicated. And it might be that we didn't catch the entire input combinations, or we didn't think about some scenario. So this is the essence part, and the essence part is complicated. So bugs can come from the essence or the accident, and they are not the same bugs. The bugs that come from the essential part are conceptual. It might be a misunderstanding of the requirements or omission. It comes from the problem domain. And it results usually with logical errors. The bugs that come from the accident part are technical. Faults in the implementation that relates to the environment, to the language, to, oh, we didn't know that the API works like that. I mean, it's not that the requirement told me to do something and I didn't understand it. I didn't know how to work with the technical part. And it creates implementation errors. And when we come to deal with each side, the tools are not exactly the same. I mean, I can say that maybe using another language can solve some of the accidental bugs, but none of the essential bugs usually, or probably. Or maybe if I use another tool, if I use smart pointers, okay, smart pointers may assist me with the accidental bugs. I will have less leaks or no leaks, but it will not assist with the essential bugs. Essential bugs come, as we said, from requirements, complicated state management. I mean, we think of something, but oh, the state that you deal here is not the right state. It's not because you didn't use the language correctly. Your model is faulty. Essence is complicated, and Fred Brooks started with that, saying that in 1986. Understanding and foreseeing all possible inputs, combination of inputs, defining the system behavior for all possible states, defining fail-safe. What happens if, okay, we realize that the system doesn't behave as it should, or I got a value from a function and the value is not in the proper range. What should we do? And in any life-critical system, life-critical systems need fail-safe, and managing fail-safe is complicated. Setting a safe path from bad state to fail-safe. So systems are complicated, which in a way is a good thing, because maybe AI would not be able to solve that part easily. We are still there to assist AI with that part. Handling the essence needs clear and actionable requirements. I mean, we need to understand the actual world. What are you trying to model? And if there are gaps in the requirements, we need to come back with questions. We need to close the gaps. We cannot assume something and then realize that our assumptions were wrong. Okay, this will lead to essential bugs. We need a good architecture, a good model of, we actually create code which is not the actual world. It imitates the world. It takes the world and then model it into the architecture of the software. So the model should be good, should fit the actual world. And we need effective validation, testing, and traceability. So when something goes wrong, we need to be able to analyze that. And testing is very important for that stuff. Accidental bugs come from a very long list. Typos. Like, for example, we had a typo in the variable name. Now, if we have a typo in variable name in Python, it would not be you would not catch it in compilation in Python because it doesn't have compilation. Maybe you will catch it in lint, okay, or maybe in runtime. If we have a typo in a variable name in C++, would we catch it in compilation always? The answer is no. It might be that the typo is that we used the name of another variable that is there. I mean, it's a typo. Oh, I didn't mean this one, I meant that one. But there is a variable with that name, okay? So everything works, and it's the proper type, or a type that is convertible too. So typos. Typos might be, we used a single equation instead of double equation for, I mean, we have warnings for things like that occasionally, but not for all cases. Or we used the wrong parens, etc. I mean, even wrong parens for curly braces instead of parens. Semantic misuse, maybe this is a semantic misuse. Semantic misuse is, okay, we used what we think is right, but no, it's not, it doesn't work like that. And usually it goes with, this is how the language works, and we didn't know that. Conversions, bad implicit or explicit conversions. Overflow and underflow. Either it is undefined behavior or it is a defined behavior, but we didn't want the integer to overflow and come back to be 0. Floating point errors, like adding too many floating points and getting an error on the cumulative rounding. Ownership and data management, we know that from C++. I mean, in other languages as well. Using uninitialized data, using dead resources, either dangling pointers or invalidated iterators, off by one errors. Out of bounds access, wrong item access. I mean, maybe I'm not out of bounds, so sanitizers will not catch it, but I'm trying to access the wrong index. It might be not off by one, it might be off by something. Resource leaks, threading and concurrency, bad API use. I mean, the API was not documented correctly, or I didn't read the documentation. I sent the arguments in wrong order. I switched between 2 arguments in the API. And critical inefficiencies, which maybe it's not an actual functional bug, but it may create bugs, or it may be non-functioning system. So too many potential bugs. I mean, maybe we should quit and let the AI handle that. It's intimidating in a way. I mean, how can we handle all those bugs? I mean, so many possible domains for creating new bugs. And the good thing is that we have safety nets. And the safety nets are many, are compiler warnings. Compiler warnings are good. I mean, I would start with compiler errors, but of course, if we have errors, so we do not have a system, and then we fix it. But compiler warnings are anything that the compiler can see that is suspicious or wrong and can help us with, okay, you have something bad. And you know that W_all, minus W_all is not all. If you're using minus W_all and you say, okay, I'm covered, I'm using minus W_all, so I will get all relevant warnings, it's not enough. I will give you an example. Here is a PTR, which is initialized to null PTR, and then I'm dereferencing it, which is a null PTR dereference. Now, the compiler doesn't have to check that, because the compiler doesn't check our code. But the compiler can see it, and you still don't get any warning if you're using minus W_all and minus W extra even. But you can get a warning. I mean, the compiler is not obliged to give you a warning. If it is not on the same compilation unit, of course, the compiler would not see it. But if it is in the same function, or maybe even in the same compilation unit, and the compiler can see it, it can warn. But you need the proper warning flag. And the proper warning flag on GCC is minus W null dereference, which again doesn't guarantee the warning, but say, okay, if I will see it, I will warn. Without that, the compiler say, you didn't ask it. And I would say, do ask it. Why? Because it's a safety net. And the compiler warnings that you should use are not only minus W_all and minus W extra. This is what I would recommend. It's a long list of things that are not included in -W all and -W extra, and you may want to use them because they do have value. Now, the reason that people do not use them usually or use only part of them are either maybe we do not know or legacy code. Maybe we have too many false positives on legacy code that, oh, it's okay there. And then maybe if we do use all these, then we work with warnings that we just ignore, which is a bad thing. So I would recommend in this case to compile old code and new code separately and use different flags. I mean, you could do that. You can say, okay, I will compile these files with more warnings and these files with less warnings. Why? Because this is new code. And in new code, I want to be more restrictive. And then maybe I can go back to old code and fix that as well, regarding, of course, depending on the amount of legacy code. But anyhow, -WL is not enough. Static code analyzers. Static code analyzers can find issues between compilation units. I mean, it may see that, oh, you're passing a pointer, which I see that nowhere is being initialized or is initialized by null PTR, and you're using it in another compilation unit in a function that doesn't check for null, and you will get a warning on that. So static analyzers is something that you should use. If you are not using any static analyzer, start doing it today. I mean, write back an email to the team saying we should start using static code analyzers. Runtime sanitizers. Runtime sanitizers check our code on runtime. We'll discuss that later on. Testing, that's important. I mean, testing. Testing is the tool not only for the accidental bugs, but also for the essential bugs. And as I said, even if I use all the proper tools, the essential bugs would not be caught without proper testing. And proper testing means proper unit testing, proper system testing, etc. And we'll say a bit more about that. Best practices. Best practices are list of things that we should follow in order to make sure that our code is fine. Now, when we follow them, in a way we omit possible bugs. Why? Because somebody realized that doing something this way and not the other way reduces the chances for a certain bug. So following best practices is good. And you can do that through code review or when you write the code. Code review is important because somebody else who is not me who wrote the code is saying, oh, there is something suspicious. Can you explain what we're doing here? And then we can catch bugs. And of course, for that, code review must be with a real showstopper ability. I mean, if you always go to a code review and you get, oh, we should do that like that, but okay, let's merge. And in no case the code review actually stops the push, then something is bad. AI reviews. Do you do AI reviews? Do you ask the AI, go over the code and say if you see something bad, do that? At this point, my advice is do that, but usually do not ask it and please fix the code. And even if you say, okay, what should be the fix, don't rush to, press the accept all green button in Copilot. Just read what are the suggestions. In some cases, they are wrong. Pair programming. Coverage matrix. Coverage on requirements, testing code would find redundant code that is not needed because it's not in requirements, or requirements that are not actually in tests and then maybe are not actually in code. Continuous integration allows us to find things ahead. So we have regression testing and we find it during the nightly build. And protective programming. Protective programming means that even if something, oh, we know it's fine, this should be fine. And then somebody says, how are you sure? Oh, because we get it from the other team. They check. I'm not sure that they check. No, they should check. Maybe we should check again. So protective programming says, if you're not sure, add something there so you will catch it at least in testing, which is better than finding the problems in production. Now in CPP, a word about protective programming in C++, in CPP North 2025, like this year, a few months ago, there was a talk by Tony Van Erd, a great speaker. This is a link. I will share later the slides. You can just press the link. This is the link to the talk. And the title of the talk was, should we check for null? I mean, the actual title was, should we check for null here? I just summarized it. Should we check for null? And it started with the answer, it depends. Why? Because maybe it's expensive. I mean, I don't want to check for null in all the path because I checked at the beginning. Why should I check again and again and again? Once I checked it at the start of the flow, then I know that it is not null, and I don't want to check again and again. It is not performance-wise. It's not smart. But the answer is you should check. I mean, there is a way to check which is not so costly, and the way is assertions. Add an assert. So if I'm in C+26, and I think there will be today talks about contracts, it might be a contract. So if we would move to 26, there would be a contract that can be headed, but if not, then assert in the function. And assert says something in the code. I assume that it is not null. If not, I will catch it, I hope, in testing. There is a message in that. I will take questions at the end. You can take the slide number, it is 31. So let's take a few examples when the safety nets actually work, okay? When we actually apply the proper safety net and it does work. So let's take this very short code snippet. You know that actually, usually bugs hide themselves quite well because they come in a big code environment, in a big code base. So here it is very small, so you can see the bug, okay? What is the bug? There is a semicolon. And the problem is that, okay, you're doing the if always. The body of the if is being called always because there is a semicolon after the if. And I guess that you will say, okay, but this is bug that wouldn't happen. It did. Anyhow, safety nets would catch it with a proper warning. And in this case, -WL minus W extra is enough. And then you can ask, so how did it happen actually in production? Because the warning level was not that. And I will tell you that it actually happened. Static code analysis like Clang Tidy also points at that. But it might be that you suppress this warning. Why? Because it might be that you do have places in code that you do put a semicolon, I don't know why, like that, okay? So the way to do it is to say, okay, maybe there is a reason for that, but I don't want to do it because it's smelly. It's a code smell. And once I do it, even if there is a reason at that place, maybe I can write it differently. And then I can say that any time that I see that, it is wrong. And then I can put back the static code analysis rule. I mean, don't do it. I mean, even if you say, no, it's okay here. No, it's not okay. It's a code smell. And maybe the next one would see it, would think, oh, there is a semicolon which is bad, and you did have a reason for the semicolon. A comment is not enough. They will not read the comment. So just write it another way, or maybe it was a bug. So there was an actual bug. This one is my blog post from 2010. By the way, it was in Java. It was in Java code. And in Java also, the compiler back then didn't give a warning. After we found it, we applied a static analyzer, which was find bugs back then, which do complain, do warn about this issue. And it actually created a memory leak. You know that in Java you can actually create memory leaks? It's easy. You just create resources and still hold them. And the thing was that there was an if, and in the if that or maybe in the else, or we didn't reach code, or we always reached code that created resources without releasing them. So there was some map holding an additional resource instead of releasing it, because we went into the wrong branch because of a semicolon. And it went to production, by the way. We found the bug in production because of a semicolon. It may actually happen. Now, the solution is easy. Just apply the proper tools. I mean, warnings, static code analysis, it shouldn't happen. Okay, let's take another example. What's wrong here? Okay, we have a point. The point has x, y, a constructor, and in main we create a point. What is the x and y of this point? The x and y are? No, I put 1 and 2. So the x and y are 2 and 0. X is 2 and y is 0. Yes, this is what happens. And the code is, I mean, compilation-wise, the code is legal. It is legal. What happens here is that we're using the comma operator. The comma operator just ignores all things that are before the last comma and then returns the last value after the comma. So the expression of params with 1, 2 is actually the number 2. So point P gets 2, and since we have default arguments, default values for x and y, x got its 2, and y gets the default 0. And we have a few problems here. The first problem is that we do the initialization with the params instead of curly braces. With curly braces, by the way, it works correctly. Curly braces would just, send the 1 and 2. Or maybe you should omit the equal sign. And I would say that also having the constructor with defaults for both x and y is bad. I would prefer having 2 constructors overloading, one that requires both x and y, and another one that says I don't get no x, no y. So I just initialize both with 0. Having the possibility, allowing the user to send only x is something that I would say is pointless. I don't see any point with that. So I would go, usually I tend to think over the years that default parameters are a bad thing. Usually I prefer overloading. Maybe explicit can assist here as well. Anyhow, but we have safety nets. We get a compiler warning with minus W all and minus W extra, we had it. And static code analyzer, in this case, Clang Tidy, actually warns on that. Use warnings and static analyzer. You may do that. I'm not, it's okay if somebody does that. It's not okay if somebody does that and it gets pushed into production. Okay, but the safety net doesn't work always. And that's the issue. Code may look fine or actually be fine, but without any compiler warning, and still something is wrong, or maybe the actual warning is suppressed. Why? Because it gave us too many false positives. And might be that something creates undefined behavior, that we can use a sanitizer, fsanitize for undefined, but maybe we didn't. Or maybe the undefined sanitizer didn't catch that. There is a very nice talk about alignment later on by Tomer Froman, and it's a 30-minute talk. I really recommend that one because things that maybe we do not do right. Think about attending that, and it may create undefined behaviors that the compiler is okay with because this is undefined behavior. Undefined behavior is something that the compiler is not obliged to say, oh, there is an issue, because if there is an issue, it's a computation error. It's not undefined. And still the code is not fine. And not all issues are detected in testing in case we didn't test all the proper scenarios. Like, for example, we forgot to test error cases. We need to test all possible relevant flows. Let's take a code example. What's the issue in this one? I have a foo function that gets I and j. I have f1 and f2 that do something with, in this case, a global variable, but you can assume that it is a data member of an object, okay? And then I pass to foo the result of f1 and f2. So the problem here is that the call to f1 and f2, the order of call is unspecified. It's not undefined, by the way. It is fine. The compiler says, you know what? Yeah, let's take it. No warning. Even if you use sanitizer undefined, it's defined. It's defined to do what the compiler wants to. Okay. Now I ran it with GCC and Clang. I got 2 different results, and it depends also, I guess, on optimization flags. And you can compile it now. You compile it again with a compiler new version or another flag, different results. What does it mean about testing? We can do that without realizing that we are doing something which is compiler dependent or unspecified, which means that maybe we'll get another result if we compile again with different flags or a different compiler. So what should we do? What is the message? Certify always. Certify things. Certify after you rebuild with another flag. I mean, do not say, oh, we didn't do anything, we just rebuild. Okay, we tested, last week. Nothing done, just rebuild. Whoa, rebuild is something. Did you change something in your build script? No, nothing, just a small flag. Okay, certify. You cannot push it, you cannot send it to production, okay? Why? Something might change. In a big system, something will change. Okay, safety nets, nothing. The compiler is fine with it. I mean, because it is unspecified, but maybe, in some cases you say, I'm okay with either, I don't really care. You should care. Okay, what's wrong here? It might be the static analyzer would. It might be, yeah. But again, it depends on whether I suppressed the proper warning, the actual static analyzer that I'm using. It might be the static analyzer would catch the previous one. What's the issue here? I presented something like that in previous talks. It's not my example. I will point you to the source of the example. Let me explain the function. There is a function called, the name of the function is get or default. The function name is on the second line, get or default. Get or default gets a map, the key that I want to retrieve, and if the key is not in the map, I want to retrieve the value associated with this key, and if the key is not in the map, then the third argument sent to the function is the default value. So you are actually asking, okay, I want the value for this key, and if this key is not in the map, bring me back this default, okay? And the implementation is quite simple. Now I have answers. Maybe the map can be empty and that may create a bug, or maybe there might be optionally dangling reference in this example, or inefficiency, or maybe the code is too generic and may work incorrectly in some cases. What do you say? And the answer is, you may have here a dangling reference. And the reason for you may have a dangling reference is that because we return, in some cases, the default value. And the default value returns as a reference. You can see on the return type that we return a mapped type by reference, okay? Now it's okay to return by reference something that we got by reference. We got the default value by reference, and we return it by reference, that's okay. But then the caller may take back the result and hold it as a reference instead of a copy. Why? Performance. The caller may say, okay, I get back the value, I just hold it as a reference, and then I use it on the second line, on the next line. Now, between the line that I get back the reference and the next line, this reference may die. Why? In which case? If the default value provided is our value, like in this case. Okay, so we have a get or default. This is my map. I want to look for the key Picataro, and the value is pineapple, and the pineapple is not a string, but it can create a string. How can I create a L value reference from a R value reference? You cannot, but you can bind a const L value to an R value. So this is a known problem. The fact that I can bind an R value to a const L value means that, oh, the function actually got a reference that the function thinks is an L value, but if I return it, it's a temporary. And then if I just take the reference on the first line, you see that I take back the reference, on the next line, the reference is dead. Now you can catch it with address sanitizer. Address sanitizer will see it, but you have to test it with address sanitizer. It might be that static code analyzer will see it. It depends on your actual tool and the warnings that you use. This example comes from a very good talk by Louis Brandy from Facebook. The talk is called Curiously Recurring Bugs at Facebook. Do you have recurring bugs in your project? A recurring bug is a bug that you fix, and then a few weeks later, somebody else does the same bug in the same function or elsewhere. And you say, oh, I thought that I fixed this bug. Oh, it's a new one. It's the same one, but again. And usually the reason is that there is, some logic in the bug. Somebody thinks that this is a good thing. How do we fight recurring bugs? We document them, and then we give a talk, right? In the company or in a conference. So documenting them, not in the code itself. Putting a comment in the code saying, oh, avoid this bug. nobody reads this comment, and maybe, okay, they will not do the bug here, they will do it elsewhere where the comment is not there. Educate your teammates. It's a good talk. It gives other examples of bugs that happened in Facebook and how they found them and solved them. So in exploration of real-world issues, I published this survey asking people, can you please tell me about bugs that happened to you? And I got many, a few examples that I'm using here. I suggested those who want to get attribution, I will, give the attribution for them, and it will come in the examples. What's the problem in this code? So I will tell you what we have here. There is a function called average. I want to calculate the average. I use the standard algorithm accumulate. The call to accumulate is fine, but if the count is 0, okay, if the count is 0, then, we don't want to do anything. First, I think that the order might be not so good because you should check first. Anyhow, the problem is that, do you see the problem with the if? I mean, checking it before is an efficiency issue. I mean, I do the division only after, so it's okay. I mean, the problem is that we want to throw an exception and we forgot the word throw. Right? Bugs tend to be stupid in some cases. It's a real report. Somebody sent it to me as, we got that. I mean, this is something that happened in our code. Now, it was not compilation error. So no compiler warning. In their case, static code analysis didn't catch that for some reason. It might be that another tool or a later version of the static analyzer would catch it. But in their case, it will not. It was caught in code review. Now, it means that if it would actually go to production, there wouldn't be there would be a crash because we actually do not throw. If we do not throw, we just create a temporary exception object, and that's it. I mean, now another way to catch it, which is not code review, is testing. I mean, did you test it with 0 elements? No, I not. Yeah, you need to. No, but I have an exception. You have to check that the exception is being thrown. I mean, you cannot assume that everything works. This is the idea of testing. So testing is the right thing to do, and the contributor is Alex Cohn. What's the problem with this code? So the story is, I will take a question in the end, write down the slide number. Okay, we have, let's assume that. Class A had a function foo, which was const. Only one, the first one. B had an override for the same one. And then somebody realized that A may need an overload for the non-const case. So somebody added the second function in A later on in the process. Said, oh, I think that A would need, maybe I see a case where, oh, I need for A also the non-const version. Okay, what actually happens? The behavior of main changed, and not in the way that you wanted, probably. Okay, let's take a look in main. We have a B. Then we point to B with an A pointer. And then we call foo. Now, since we actually hold a B, we assume that the foo that would be called would be the right one. I mean, it's a virtual function, and I'm B. And actually, in this example, the foo that would be called is the foo of A. Why? Because it's a non-const object. And then the compiler says, okay, you are non-const, so I prefer the non-const signature. So it looks at the non-const signature, which is a foo with no const, the second one. And so when we added that, we now go to the A foo, the non-const one, just because we added something in A. Now, there may be other solutions, like maybe you should add the one also in B, or maybe you should think about when you add something in the base class. By the way, there is a best practice saying non-leaf classes should be abstract. So, oh, why should I have an actual implementation, or maybe even it should be interface? I mean, there is You added something in A because you thought that maybe you have an object of type A. Oh, why do you have an object of type A, which is a non-leaf class? So maybe there is a design issue. Anyhow, that's a problem. No compiler warning, code analysis in this case didn't catch it. I mean, it may warn, but in this case it didn't. And again, it depends on the actual tool and warning level. It might be that in other cases it will. Maybe AI would warn. In this case, it was discovered in production. Again, it was reported by a person on, oh, we add that. Now, they didn't, the function in their case was not called foo. Otherwise, I would say, and they have a very strange name for the functions, but I just, shortened the example. Mitigation, either add both, and of course, have a test case. I mean, if I have a test case for the thing, and then I realize that, oh, in my test, I don't go anymore to the proper function, I go to the wrong function, I realize that something is wrong. Other polymorphism issues, different default values on virtual functions. I would not go through each one of the links, but you can think about that. Forgetting virtual destructor. We get warning on that usually. Forgetting adding virtual on a base class destructor. Calling a virtual function from constructor or destructor. You know that calling a virtual function from constructor or destructor is not polymorphic, but it is allowed. And in some cases you say, no, it's okay, I know what I'm doing. But when somebody reviews your code, they would not know whether you knew what you're doing or, oh, there is a bug here. So a best practice is just to avoid it. I mean, in some cases you say, no, it's okay. Find another way to do it. Otherwise, you're now doing something that in some cases would be wrong and hard to discover. So it is better to say, no, we do not allow that, which is a best practice. Okay, this is a bit long, but I can tell you, there is a car screw here, and I will just go to the main, and main holds 3 shared pointers. Each one holds the other, so we have a cycle of shared pointers, and the problem is memory leak. You know that you can create memory leaks even if you are using smart pointers, and the reason is that all 3, even if nobody holds any one of them, they hold each other. It's a very known problem of, okay, we have a dependency cycle of shared pointers. Now, usually it happens with, oh, I have A, and I'm using a shared PTR of A that holds B, and B holds C. Everything is fine. If A dies, the others would die as well. If B dies, C would die. But then somebody realizes that maybe C needs to hold A. Oh, I need C to hold A. Okay, so I will hold in C a shared PTR to A, which is fine because A was born as shared PTR. You have a leak. And the solution is to use weak PTR. Now we know that, but in this case, no compiler warning. Other sanitizer should catch it because there is a leak. Other sanitizers see leaks at the end of the run. And it actually happened. Another example, it's a bit long, so I will just explain briefly what is going here. We have a function that writes into a buffer or into file, in this case, a number. And the number that we got is the second argument, the input. But it might be that the input is binary or text. So we got a number. The number might be the digits 1, 2, 3, or it might be the 4 bytes of the integer that represents 1, 2, 3 as a binary form, okay? And the function wants to handle both cases. So we check. If it is binary, just get the binary into output, and then we'll write output into the file because the file wants to get binary. That's easy. And then we have the else. The else is for the case, oh, we got text. So in the else, we say, okay, we'll just stream it into a string stream. Then we will just, put it into we have here a string stream with the input. We create the value. Then we put it into the value, which is the actual type that we wanted to create. Let's assume it's int, okay? And then we ask output to point to value. Okay, output, you're now pointing to value, okay? And then eventually, we write output to the file. Do you see the issue? The compiler doesn't. Yeah, there is a dangling pointer here. Output points to value. Value is a local variable of the close of the else. When you end the else, the value, local variable, is dead. But it works. Why it works? Because it's on the stack, and I still point at it. And the problem is that with things that work, I mean, it passes the tests until in production for some reason, I don't know, maybe not in production. Maybe you change something and then the stack behaves differently because there is a new variable being created for some reason. Oh, and now I get the wrong value. You shouldn't use something that is dead, even if it works. So this came from a real actual report, not the actual exact thing. It was a bit more complicated, but I just put it in one slide. There wasn't any compiler warning. Other sanitizer would catch it. I mean, other sanitizer sees when you try to reach something out of stack. I mean, it's beyond the stack, but it depends whether you actually run it with other sanitizer. It may become a security breach. And in this case, it was coded by a static analyzer. What's the problem with this one? I have a widget. And the widget has a string. And I will also have a getString function, and there is a function that wants a string in the widget, and in main, I send the string, and I want to send the widget, but because I don't use the widget anymore, why not just move it? So I move it. So first, I don't know the order. The order might be any. But I would tell you that it doesn't really matter what is the order. In each order, it is wrong. Because I take the reference to the string. Either it is I first take the reference or later. It doesn't really matter. You are holding a reference to a moved from object. I mean, the string is a string, a reference to a string on an object that was moved from. And you went through the move constructor, or yeah, it is a move constructor of widget, which is the default move constructor that calls the move constructor of its members, and the move constructor of a string invalidates the original string. So I have an invalidated string, and that's a bug. That's not good. So, okay, I have a suggestion. Maybe the getString function would just return by value. Okay, what's the issue now? I mean, I return by value. It's a value. Now it depends on the order of evaluation. So if we first call getString, we get a copy of the string, we are fine, and then we move from. But if we first move from, then, we moved from, we get a copy. But a copy of something that was moved from. So now we have an issue that depends on the actual order of evaluation. Now, it might be that it works. It might be that even maybe the static analyzer cannot catch it, maybe because of small string optimization. It might be that we actually do not point to the string on the heap. The string is still alive. A moved from object is still alive. But it is like moved from. And the string, if it was a small string, then the small string is still there, but like there isn't any allocation that was taken. So, and there isn't any null saying, I don't have the allocation anymore. I just have, it's, do you know the small string optimization? So the problem is that if it is small string optimization, it would work. I mean, I wouldn't catch the problem. And the issue is that in some cases, we test things with small strings, and then, in production, then come the big strings. Just, to make the life harder. I don't know why. Why do you come with long strings? Why don't you? So the moral here is to test also with both small strings and big strings. Like you have something that gets a string, that uses a string, then have a test with a small one, have a test with one that is more than 16 characters usually. Okay. And in this case, it was caught in testing, but again, if it is a small string, it might be that it will not be catched. What can be the problem here? I will tell you what is going here. Okay, so we have some mechanics of we want to register a factory for any type that we need a factory for. So we have a function, register factory, that uses a trick of I'm creating a static variable. So if I call it twice on the same type, then the static variable will not be created twice. It's a way like to create a singleton in a way. So I take t, and since it is the t is spreading the function, the template is being created per each type t, then any new t that was not introduced before would create the factory for the t, okay? Now in main, I register factory for a, okay? A was created. There is a factory for a. I register a factory for b, and then I realized that when I register a factory for c, It was not created. C didn't get its factory in this case. Again, something that actually happened to someone. And then they realized that C was a type def. A type def is not a new type. They wanted something for C, but C was a type def. Then when it comes to the template realizes that, oh, I met C already because I met B, and C is a type def for B. Now they do want the factory also for C. They didn't get it, okay? That's an issue. And the reason any compiler warning, because it works as designed. I mean, this is what you wanted. This is an accidental bug. We didn't use the language correctly. I mean, the language that does what we asked for. And static code analyzer wouldn't catch it because, you know, it's in the code. It's how we ask things to work. And the mitigation was, you know, find it in testing and keep things simple. There was a trick there, and the trick was bad. So if you have some kind of a trick, just, you know, make sure that, or maybe, you know, you can just go in main, and in main, register all the factors that you want, line by line. You see it? I have your 9 factories. It works. Why should I need, you know, this trick that doesn't actually work? And again, this was reported by Ronen Friedman on a bit more complicated example, but the idea was what we just presented. Okay, what's the problem with this one? Yeah, it is too complicated. Yes, that it is. Yeah. So you actually cannot say, do we have a bug here? And the answer would be, maybe. And somebody else will say, for sure. I can just, you know, point arbitrarily somewhere and probably there is a bug there. I can see bugs. Can you see bugs? I can see. Okay, take a look at the right upper corner. Do you see the return value on the right upper corner? Return direction, colon, colon, R. I assume that R comes for right. What is the comment? I guess that AI can say something about that. AI would say the comment doesn't correspond, the comment doesn't fit the actual code. Do you see the one before the last, the return in the else, direction up left, UL? What is in the comment? Somebody did their copy paste, then maybe they changed the code but not the comment, or maybe they changed the comment but not the code. Anyhow, there is a mess here, and the mess is related to this is a bad way to implement, I don't know, working with enums, what is the logic? What are you trying to achieve here? And usually having a small functions, something that is easier to maintain, and I understand what is the logic, because even if I wrote it and I come later to it, I would say, I don't know, I don't remember what is the logic here. So complicated code is something bad. And what about that one? Again, same enum in a way. No, not the exact same enum, another one. So I'm looking at that and I see, okay, hard-coded numbers, magic numbers. I'm not sure that I return the actual proper enum in each case. I return the same thing in some cases. Yeah, 8 right twice. Is it good? I don't know. It might be, but I cannot tell. It's hard. It's hard to tell. So it might be that we could have implement the logic in a way that when I read the logic, I understand what is going on there, and then I can realize whether it actually works as I need or not. And it might be that it works. I mean, it passes all tests. But even if it passes all tests, when I come to that, I say, okay, you don't have bug now. You will have one at a certain point. I can tell you, okay? The bug will come in. You see code smell. And when you see code smell, then you need, it comes from the book refactoring, then you need refactoring. When something doesn't look well in the code, it means that, okay, well, the next one would touch this code, will introduce a bug. High chances. So there is a very nice talk, a lightning talk in CPPCon 2017 by Michael Matrosov, refactor or die. Let's assume that there is a probability of, oh, we have a bug. Now you can like analyze what is the probability. At a certain moment you say, oh, I have a 1 probability. 100% that I have a bug here. Why? Because the code was complicated and we just, you know, added more and more stuff into the code. So I can tell you there is a bug there. You should have refactored before. And the way to refactor is to have proper unit testing and then try to, I mean, you should keep the same API, but change the internal of the function to make it simpler. What's the problem in this one, which is, again, a bit complicated? Yeah, there are too many nested if statements. If you are following Misra, for example, I think that I have one or two more than Misra allows. I mean, there are code standards that say you should not have more than 2 nested ifs. And when you see too many nested ifs, in this case, it means that I'm trying to manage, what I'm trying to manage here, which is not the right way. You should not manage it like that. I'm trying to manage a state in a very complicated way, and I'm coming to a state hell. Like, oh, what is state? Oh, we should do that. Oh, wait, we should check that also before, and then maybe we should do that. Or in this case, we should do that. And when you come to a state hell, the proper way to handle it is a state machine. You should refactor that state hell into a state machine. Now, the state machine, the idea of a state machine is that you look at the requirements, and the requirements say, if you're in a terminate state, this is how it should work. If you're in a cancel state, this is how it should work. If you are in a, I don't know, opening, then you should model that the same way. Now, when you try to catch them all with if statements, and you say, no, but in all 3 cases, I do something which is similar, so let's put that outside, that's a state hell. I mean, instead, having a different isolated state per each one would have a very isolated part of code for each state, and you know what you are doing there, and you can check it with the requirements, and you can test it. It's much easier. Other significant issues, API issues, like API is not working as documented. Let's assume that API doesn't work as documented. Is it your fault? Is it your fault? No, but what should we do when the API doesn't work as we assumed? We caught that. Okay, there is a problem. API didn't work as we assumed. Then you should ask questions. You should look for, do we have tests for this API? Maybe not my test. Maybe the API came with tests. Maybe it's the API of the other team. Did you test your API? Is it according to what we realized? Now, another thing that you can do is to add a facade. Once I have a facade to the API, maybe the API is fine, but I switch between arguments because the API doesn't use strong types. I want to use strong types. I want to send distance. I don't want to send 7. I want to send an object with measurement units, but the API doesn't take that. It takes 7. It takes number. So I have a facade. The facade will take my types. A facade is part of my code. And then in a certain one place in code, there would be all the mitigations to the other API, which I don't like so much. But then if there is an issue, I can find it and fix it in one place. And then I can add logs and other things there. So protected programming before I go to the API, after I get something from the API. You know that there is a famous bug of radiation system that sends too high radiation to patients. And the problem is that, okay, there was a hardware issue maybe, and there was a software issue, but before you actually send the command of, okay, I want to send radiation, check if the number is in between the proper range. And if it is not, just stop. Okay, so you cannot rely on, oh, the API said this is the number. Okay, but before I use the number, let's be protective. Bend memory access. So use the proper tools. Ask a question. Is the iterator invalidated? Don't hold an iterator, then do a pushback on a vector, then continue using it. It may work in testing because the pushback didn't enlarge the capacity. But in production, there would be a few calls to pushback and the iterator would be invalidated. Or maybe you have tests that call more than one pushback. So testing. And of course, it might be that you'll catch it in an analyzer, but it depends on, did you test it correctly? The language becomes a bit more complicated. I will give you an example. For each, for ranges, can you see the signature for each for ranges? It's complicated. So this is, in a way, a source for bugs. When something is a bit more complicated, it's a source for bug. And the solution is try to distinguish between frameworks and user code. Frameworks might be complicated. User code, the code that I write, not as a framework developer, should be easy. I don't need to support something that complicates the code, which is not actually required. Otherwise, bugs will come. Let's summarize. Programming is tricky. we should mind the traps, be aware of pitfalls, and we cannot memorize all pitfalls. And even if we will, a new one will come. So we need to use the proper tools. But still, be explicit, prefer safe constructs like RAI, strong typing, and of course, small functions, stateless, over stateful when we can. Review and refactor, use the proper tools, compiler warning, static analysis, runtime sanitizers, code reviews, and of course, testing. Additional resources, currently recurring bugs in Facebook. I recommend this talk. I have another talk on typical type typos from 2021 ACCU, other examples of bugs that may occur. Thought on enums. So you thought C++ enums, so you thought C++ was weird. Meet enums. Enums are a source for bugs, a lot of bugs. I mean, somebody come in and needs a new value in the enum. Add something in. There will be a bug because of that. I mean, you have to be very careful with your enums and have proper tests for, oh, if somebody adds an additional enum, maybe I should catch it in testing. Acknowledgements to those who reported bugs and discuss them with me. If you want to report a bug, I can use it for later talks. You can take the QR or speak with me. I will share the slides later on, and that's it for my side. I'm ready to take questions. I told you that the questions will be on the break. I know we just overtime, but still I'll start with 2 questions, and then anybody who wants to be here for additional ones. Udi. 63. Okay, going back to 63. Yes, I'm here. I'm checking it on, I'm having an assert on the first line of the function.
No, but there still might be bug intention, because if it's a char, unsame char, or side char, it still will be.
Oh, I think that you had a lightning talk on that. There is a difference between signed char and unsigned char. There is an issue here. Things are complicated. That's correct. 60. Okay. We have bugs in the bugs.
No, this is not a bug in the bug.
Okay.
Number 4, calling virtual function from CTO auditor. You can do this. If you do this, you can use the qualify them using the class name.
Oh, you say that, okay, if you do that and you show that you know what you're doing by calling the function with the same class, colon, then in a way you like say to the reader, I know what I'm doing, okay?
Add a comment to say that.
And also add a comment. Okay, I'm good with that. But if you do not, then the reader doesn't know whether you actually knew that, okay, I'm calling the same level, or you thought that this is polymorphic. I will take a comment from another person, yes? Object slicing. You want to see the example? Okay, so I will just start with what is object slicing. I'm doing something with an object, but the compiler doesn't see that I'm using the inherited class. It thinks that I'm using the base class. So only the base class part is being handled. And a very known example is like assignment. Let's take a look. Oh, I don't have internet because I didn't check that the links work. Anyhow, it will be there. I can tell you the example. The example is simple. Let's assume that I have a pointer that points to a B, but the pointer type is A star. Then I do an assignment on the deref of A. Which assignment operator would be called, the A or the B? The answer, the A, unless the assignment operator is virtual, which technically can be, but doesn't actually work as should. It doesn't actually work as you want. So it is a problem with the quality, with assignment, with the quality, with anything that you say, oh, I thought that it will call the proper function. No, it calls, it's not a virtual function. And even if it is, it doesn't work, because virtual functions work on the caller, but what if I have the same issue not on the left side, but on the right side, on the argument? Then again, it is slicing on the right side. And slicing happens. I mean, in some cases, oh, it didn't call, or it took only the A data and not the B data. Yeah, because it thought it is an A. I will stay here for any other comment or question. Thank you very much. There is a coffee break, and I'm here. Thanks.